Okay, so good afternoon. Today is lecture 30, and this will be our last lecture on small oscillations. And we'll just tie up some loose ends. The basic ideas which we have worked out are fine. So let's just get started. Uh, so this lecture, what we're going to do is we will prove that there are as many eigenvectors as there are eigenvalues. As many eigenvectors as there are eigenvalues. Okay. So by as many eigenvectors, we mean linearly independent eigenvectors. Okay. So this is the proof. And last lecture, I had some issues with this proof. I mean, I gave a proof which is correct, but I mean, I didn't prove that it was correct. I mean, it's almost correct. I mean, so we have to see how that goes. So, so, so we have some. So recall that we have some complicated Lagrangian, which would be t plus v, t minus v. Okay. And so let's say that there are q1, q2, up to qn. So some capital n dimensional phase space, I mean coordinate space, set of coordinates, so 2n dimensional phase space. So we have t and v, and and there is some fixed point. Which we are saying is stable. Okay. And so last time I put, I think, zeros here, I guess. Let me actually, I think better notation would be to put a zero on top as a superscript. Today I was. Okay. And of course, all the q dots are zero. That's so because it should be, this is a fixed point. Okay. And the assumption is that it is stable. Okay. So let's so this is what we have. L could be horribly nonlinear, but the idea was that we approximated the neighborhood of the fixed point. As follows. Again, this is something we have done. We just say that L some particular form. Okay. And this will take its values at so the approximation is to discard these. So first thing to understand, to go back, and I'm just summarizing things. So that means stability, there's a few things. So stability requires that Vij. So first thing is both first thing is that both Tij and Vij are symmetric. With no loss of generality, they are symmetric. Even if there was an antisymmetric part in this, because of the symmetry of these two guys, it will be considered. That is one thing. They're also positive definite. This is what it means. So it means that their eigenvalues So a matrix is positive definite is if you know vi j eta I eta j is always greater than 0 for all eta I eta j for all eta. So you pick a eta I and then you plug it in here, it's positive. But it also means in terms of eigenvalues equivalently. What can we say about its eigenvalues? Not positive. So this is these are the things which we are given. Okay. So then if you remember that the eigenvalue equation, okay, so we said that and define this matrix T to be Gij at Q naught of course and V to be Ij. Then the equations tell you that minus omega square T minus V det of this should be 0. Okay. So far, any questions with notation, etc. plus? Okay. So what we yes.
Sir, in your notation, you were taking it to be minus V.
No. Today I think I've changed notation. I cheated. I put minus here correctly. Everything.
Oh, okay.
Okay. So yeah. So this is correct for today's notation. Sorry about it. Right? Yeah. That day I did something. I don't know why. I just defined things. Okay. So this is what we have, and so we solve for this and we get eigenvalues, and that's not a problem. And but the thing is to show. So we need to prove that. So this determines the eigenvalues. Okay, so let's say we'll call that A. A goes from 1 to n. Okay. So what we want to do is to so the eigenvectors will satisfy this equation minus omega A square minus V plus V acting on some vector, which would be eta 1 to eta n, or I call it A1 to AN plus. So this is what we call an eigenvector with eigenvalue omega A. Okay. So our convention is that it's always coming as omega square, so we always choose for every value of omega there's plus and minus, so we just assume that this is always positive or 0, not negative. We just make it unique. Okay, so this is what we wanted to prove, and so what we need to show is that there is a solution. So we need to show okay. So the way to do this, so life would have been easy. So trivially true if T was proportional to identity matrix. Right? Then it is a usual theorem that symmetric real matrices have eigenvectors, enough eigenvectors. Okay, so this is what it is. So is this point clear? That if you come here, and if t is proportional to some constant times identity matrix, I can absorb that constant from omega square. So it looks like the normal eigenvalue problem, and V continues to be symmetric. Okay, so now the question is, what if V is not even diagonal? Okay, so we'll do it in two steps. Then step one, make t diagonal. Okay, and that is possible. Why is that possible? It's always possible, I claim.
Diagonalization. Because
Yeah,
T is symmetric.
exactly. Because t is okay, always possible, since t is symmetric. So what you will get is, let's say that we have finished this step, and I'll call it t prime if you wish, but we just call it t. So it's enough so we have to make some change of variables, and from that we'll go to some t prime, which will start looking something like this. Say it looks like m1, m2. I'm just calling it. I'm using. So, and what can we say about m1, m2, and mn? All these n's. These are the eigenvalues of this t.
Will
What can we
be
say?
greater than equal to 0.
Yeah, they're not even equal to 0. If it is equal to 0, then it's like a degenerate t. So mi or mi are all greater than 0, not even equal. Since this is because t is non-degenerate. This is some assumption. So I'm trying to mark all the assumptions that we have. Positive definite and non-degenerate. So it's symmetric, positive definite. Okay, so then once we have done this thing, so now it suffices to consider diagonal, which is what we started yesterday, but then we tried to do T inverse, which was a mistake. So let's look at, so focus on in this new coordinates, coordinate with coordinates. Let's look at it. Let us look at kinetic energy. Okay, so it's a kinetic energy term, would look like this. Of course, T approx, that's what I mean, will be right. And we, of course, will, because it's now diagonal and you put this in, this is what we get. So what we do is, and we, of course, we will continue to be symmetric. We will be nj, wij, eta I. Okay, so these etas, by the way, are not the same etas you would have started out with. I'm using the same notation, same coordinate for that. Maybe if you want, I'll put a tilde. Let's put tilde. Okay, so this is what we have. So what I will do now is I will now define one more. So step 2, this is. Define one more set of new coordinates. Okay. I'll call them now capital Qi, and I'll define them to be root mi. Okay, I'm allowed to do this, right? It's just some Lagrangian that I have. If you come here and see what happens, you can see that T approx now in these new coordinates becomes Is this clear? Just that construction. So what I've done is taken this mi and taken square root of that and put it into this. And I can take square root of this because, and everything is real because mi is greater. So now we have, what does this do? This has made t in this new thing. So, and v approx, I should actually even put a tilde here also. V also changes. Okay, is this clear? This is what we get in this new capital coordinate, Q coordinates. Any questions? I'll pause here. Aziz, we made two steps. First step, we made t become diagonal. Second step is we did some rescaling of the coordinates. And this. Okay. Good news here is that, so let's look at this guy, this term. It is symmetric, right? Do you see that it is symmetric? Still remains symmetric.
Yes.
So
Okay.
why did we use this rescaling fact?
Because I want to map. Because think of this remark: if T was proportional to identity matrix or equal to identity matrix, then the theorem is proved. Okay. So now what we have is T double prime is just identity matrix. Okay, and V double prime is just V tilde ij divided by square root mi mj. It's symmetric.
So sir, is it like an alternative solution instead of taking inverse of the T matrix?
It's not taking because if you take the inverse of the T matrix, we are not guaranteed that V will be symmetric. T inverse V, see the problem we had yesterday was, good point. So recall that T inverse V was not symmetric. Generically. Okay. Even if T was there diagonal. So yesterday we did step 1, but in step 2 we try to take T inverse. Or we try to do step 1 and step 2 together. This doesn't work. That was a mistake. So now you can see in terms of this, the new eigenvalue equation. Eigenvector equation is a standard eigenvalue equation first. Is nothing but omega square I minus
Excuse me, sir.
yeah.
Could you please again explain that how did you write T as identity matrix? I did not get this point.
So we have T approx. This is what we call T prime, right? Where we said we have diagonalized it. So and call the diagonal. So let's look at it. In step 1 we got T prime, which was M1, M2, Mn. This part you're okay, right?
Yes.
So now I just put it into this thing, and this eta I tildes are the new coordinates. We made some change of coordinates, which is some linear combination of the etas, which is the ones which you need to make things diagonal, and then this is our current, what do you call the current T and okay, it's not yet. So it's so. You agree with this statement?
Yes, sir.
Okay. So now what I'm doing is I just see here, eta, if qi is root mi eta I tilde, then qi dot is root mi eta I tilde. So which is what you can see. I can take this into this inside here as with the root mi and write it as half qi dot square. That's what I've done here.
Yes.
Okay, so this is the same as saying T matrix is T double prime is identity, no? Let me be more pedantic. So T would be half summation ij. Identity matrix is just delta ij. Then qi dot qj dot. I can carry out the summation over say j to get.
Oh, now I understood. Yes, sir.
Okay.
Yeah.
Okay. I skipped this step. I thought it doesn't matter. Okay. So now you can see that this is a standard eigenvalue equation. Like we know, we're just finding the eigenvalues and eigenvectors of V double prime. So now, and V double prime is symmetric, and hence we obtain all the required. Okay. Of course, if eigenvalues are equal, right, then you will get a subspace in which you find an orthonormal basis and do Gram-Schmidt or whatever. Okay, that you know. So, but the key point is you will get n eigenvectors, and linearly. And we call these normal modes for n eigenvalues. End of proof. That's it. Okay, so yesterday we really messed up in step 2 because we were trying to do T inverse, which is the intuitive guess, but actually we don't need to do anything here. We just have to rescale and make it identical. Obvious, something very obvious, but well, it didn't strike me as simple as that. Okay, so the proof is done. Are you convinced at least?
Yes.
Okay. Any questions, comments?
Sir, just one question. Why have we written T as T approx? Over there, we haven't used any linearization. So
Where?
T and T approx will be the same, right? In the upper, like.
Yeah, no, it is not. That is not true. It is approx even for T. Yeah, that's a very nice question. Very, very nice question. So I'll tell you why. Okay. For generic T, even if you stick to generic kinetic energy, before approximation would be T equal to say summation. Okay. So what we are doing now, this is equal to summation ij Tij of Qx.
Oh, okay.
So there is if you expand, it's a power series. Even if you expand, even if you restrict to two derivatives, we still have to
Right.
q. There is a dependence on q here, which we are getting.
Right.
Even this an approximation. We are throwing away these terms. Right. So the next term, for instance, just in case people are wondering what that is, that would be that's the derivative. So it will be Tij of q by Tqk at q equal to q naught times, then you multiply by this, so it will be eta k. Okay, maybe I should have called this etas, but okay, you understand. So this, you can see this kind of term we are throwing out. Infinite series. Okay, so T is also approx. Is that clear? Okay, any other questions?
Yes, sir.
Okay, good. Okay, so let us do an example where we see all these ugly non-linearities, etc. So it's a nice example where we do all these truncations properly. Okay, so let me do that. So we'll just do it's a where you know this. We have looked at this I think before. So we have a double pendulum, two masses, M1, M2, L1, L2, theta 1, it's just a double pendulum. Okay, and we worked out probably did the Lagrangian at some point in time. Let me just. We did this, right? We did the Lagrangian for this.
Yes.
So let me just write the Lagrangian. Oh God, my eyes are bad. I can't even read something. Just give me a second. I must say this is truly ugly. But this is a great thing about uh, Lagrangian methods is that we don't need to worry too much about anything. So this is what we have. Okay. So so the thing is, what is a stable fixed point? This is a question to you guys. I'm sure in high school you'd have said this faster.
All of them zero.
Absolutely right. Theta 1, 0, dot, dot. Okay. So we don't need to introduce new coordinates or anything. We just need to expand and then see. So first thing is let's look at T. Okay, so let's mark things. Okay, so I won't. I'll just so theta 1, theta 2 are small. That's our thing. So we throw away all terms which are higher than theta 1. So let's look through this and look at T. So you see that this is the only term which has a dependence on angles, on coordinates. So what we can do here is, T approx. What should I replace cosine theta 1 minus theta 2 with?
1.
Exactly. Okay, because it's already ordered theta small square. So we just have to do that. So T approx, we are getting that. So let me just write that. Um, okay. So now next step is what is it we have to do for V? Right. So let's look at this. What should I replace cosine theta 1? And similarly cosine theta.
Sir, all the cos terms will be 1 now.
No, because this is we have to
Plus
keep terms
theta.
up to theta square, right?
1 plus theta square minus theta.
Okay, and the one term we can drop because it's some constant, so we won't worry about that. We'll only keep the square dependent terms. Okay, so now let me just write what is V approx. Is this fine? Again, I should be careful about signs, so it should be plus. Okay, it's T minus V, right? So that's it. This is okay. So we are set now, right? So we just need to work out what the matrices are. Is this clear? So let's see what T
Yes.
is.
Sir, in second term, V approx will be theta 2 square now.
Yeah, I know. Thank you. Any more mistakes?
No, sir.
Good.
Should be G, not G2.
Yeah, yeah. Oh, overzeal is G. Okay. Any more? Okay. So let's look at T. It is forget the half, so the half will be kept outside. So it will be M1 plus M2 L1 square, and then cross term, and V. Okay. Is this clear? So, so we have this, and we need to find. We need to solve for eigenvalues first. Is this clear? So we have substituted it here. Okay, so plus terms which have dropped here constants. Okay, so this is what we have, and So
So I don't think the minus sign will come now because we are counting.
yeah, I know there is, it's like bad habits. Thanks anymore. Okay. Okay, so we need to solve for it, but I'm not going to. I just take the answer. Okay. Okay. So is this clear? So exercise now. This is okay. So show that there are two eigenvalues. So omega 1 and 2 square will be a quadratic equation. Okay. So this source for this is Landau and Lipschitz. Okay. So of course they don't show the working either. They just give the answer because it's just solving a 2 by 2 determinant thing. So it's a quadratic, and this is the two roots of that equation. Is this clear? So that we can solve for it, and of course also obtain the two eigenvectors. Okay. So there's a nice limit we can try. We can take one particular limit. Let's say we take what happens if m1 is very, very large. So m1, we take it to be infinity or something. Okay. If we do that, let's ask what happens. And so we just track all the m1s. Okay, so here is an m1 here, there's m1 here, there's m1 here, there's m1 here, m1 here. Okay, so these terms will dominate. So then in such situations, omega 1 2 square equal to, so the m1s will disappear, g by 2 L1 L2 into m1 goes off into L1 plus L2 plus or minus this. So you can see that all these m1s will go away, cancel away, square root of L1 plus L2 minus 4 L1 L2. Okay, so all the m's disappear in this limit. The answer will be a little boring, don't get upset about it. So okay, so what is this? L1 plus L2 whole square minus 4 L1 L2.
L1 minus L2.
L1 minus L2. Very good. Okay, so we get two answers. So omega 1 will be square okay. Now looking at these values, can you tell me what this means? Do these numbers, so if I say square root of g by L2, square root of g by L1 mean anything? Okay, so let's look
It
at,
would have been the angular frequency, like independent.
yeah, so the thing is, really what we have really is saying that is M1 is much, much greater than M2. We don't need infinity. Okay, so what happens is that it just has the simple modes of a simple pendulum. So M1 is not too affected by M2, so it's like a fly on an elephant or something, so you forget about that. So M1 will have its, so one of the eigen, so this fellow is just the oscillations of M1, and M2 will be this particular, uh, the case when, so when M1 is very, very large, so it's like it's almost fixed, and so this will just oscillate as if, there are two, it's like two simple pendulums. So they behave like two. Okay, so let us try one more example, one more situation. We are looking very ugly. So let's say that M1 equal to M2, L1 equal to L2. Okay, let's do that. So we get this. Is it enough if I do M1 equal to M2? Will that be a simplification? No. Okay, so let's do that. So we get G by 2 ml squared. M1 plus M2, so it will be 2 plus 2, so it will be 4 M1, 4 ML. Is 2 M. Okay, so all the M's disappear. So we get something like G by L, 2L into, so M by 4L plus or minus. So 8L square minus 4L square is 4L square, which becomes 2L. This one is equal, so it's 2, 2, 2. Then this M should go away. Okay, so we get I can do one more cancellation. Okay, so exercise actually is, it might be exercise is to, the interesting exercise here is to do the um, okay, and see if that kind of makes sense. So, this is so are there any comments about this part? This is clear. This computation you can do other possible other calculations as well. I mean, I just did two different limits, and so I mean I don't want to sit here and do the computation of the eigenvectors. It's a little messy, or is it? Yeah, I'm not doing it. But I just want to conclude. Okay, that small oscillations only give information about situations where the amplitudes of fluctuations are. Okay, so they miss out on the physics or the behavior when the amplitudes are not changed. Okay, so then we need to include the nonlinear at the level of equations of motion, or cubic plus higher order terms. Okay, so in particular, we know that what we are getting here for small oscillations is nice periodic behavior, which is very, very nice. But you know that at large amplitude, this particular Lagrange system exhibits chaos, right? It does weird things. This is actually so in the double pendulum. We miss seeing the chaotic behavior. Okay. Now, before I stop here, I want to ask you, what is chaos? What is meant by chaotic behavior?
When small changes in initial conditions lead to large changes
Exactly.
in future
So,
time.
extreme or exponential sensitivity to initial conditions. This is what is chaos, and so we will never see that behavior when you do small oscillations. So if you have to really do these solve these equations, you can see this is not a simple. I mean, these equations are not so simple. Look at the Lagrangian, we can write the Euler-Lagrange equation for this full thing, and so the idea is that what one could do is okay, so let's look at this particular term and ask what is it we can do to improve. So here in our truncation, what we do, we stopped here at theta 1 square. So the next term here would be power 4, theta 1 power 4, theta 2 power 4. We can add that in. Similarly here, we'll get theta 1 minus theta 2 whole square. So you can ask, how do these additions, so you can so what I want to say is that maybe one can study the first set of nonlinear and ask things change. And so this is something, there are ways of doing these things. We won't study that here, but this is quite often a first this thing. So you can use some kind of perturbative solution. So let's say we got some solution. So let's say we got a solution which said that theta 1 of p is, and theta 2 of p is, so there are two eigenfunctions. So some a1, a2, e power I omega 1t plus d1, d2, e power I omega 2t. Of course, real part a1, a2, d1, d2 are imaginary, etc. All that. Do that. So this is our simple solution. So what we do is, so we call this the zeroth order solution, and then substitute this into the equation and ask for solve in perturbation for the first direction. Without that theta 1 power 4, theta 2 power 4, and theta 1 minus theta 2 power 4, this zeroth solution is exact. But now we want to put it in there, and we think of, we try to feed this back, so we write, basically theta 1, theta 2 to be theta 1 of 0, theta 2 of 0, plus, we know this, known, theta 1, 1 of p, of course. Because it's an infinite series, at least you solve for this and you study this behavior. So you study how this. Does it show chaos? I don't know. Okay. So I'll stop here. So these are things. Again, LNL, Landau Lifshitz has some preliminary discussion. Okay. But I must tell you that is one of the densest books I know. It has some. Let me look at how many pages it has.
160 or something.
Yeah, very few pages, 166 pages. And in 166 pages, he covers just about everything that you need to know in classical mechanics. And so if you can understand that whole book, and there are certain things in there which to me are mind-blowing, I mean, kind of things which are there. So it's like I probably told you in the beginning, it's at a higher level, but it's worth taking a read. Okay, so read it like you would read a novel. Okay, so you should know the stuff, and then you read it, and then suddenly you should hit something which will make you go, stop reading it like a novel, open a book or get a pen and a piece of paper, and you start playing and try to understand the things he's saying. And all standard problem, he'll make it into a problem, but every problem has something in it. So it's just this mind-blowing book. Only 166 pages, but I mean, it's one of the densest books, like I said. So I'm done for today, and I'm done with small oscillations, and we will start working towards special relativity. But next lecture will be on Lie groups, Lie algebras, things which we know, but I will make it kind of know. So, for instance, we saw something last. We saw that R TTR R inverse was antisymmetric. Why or how? Okay. So this is a very beautiful structure. So R is related to what are called Lie groups, while these antisymmetric matrices A, let's call them the early algebra. And so these are like small, this is finite or large. We will see all these things. Okay. So this is the start of this thing. So I will need this material for later when we are going to, we will, we'll sort of see how you could have derived special relativity in high school. So we will do it at the level of high school, or maybe, I mean, maybe I'm being very tough, but actually maybe first year BSc level. We will see that the kind of things which we knew will be in direct conflict with the Galilean group, etc. And we will see how that will go. Okay. So this, so I will need some of these ideas later to, it's like what we are, the first part of thing will be like taking a single in cricket, but then the connection with Lie groups will be like hitting a six as Einstein did. So we will see the sixer part as well. Okay. So I'll stop here.